you ever wondered exactly how a local infection become a global pandemic or how a single opinion cascade into a viral movement? The answer lies in network diffusion. Today our team, Yashashvi, Harsh, Hitesh, is excited to present NDlib. NDlib is a powerful Python toolkit designed to simulate these complex spreading processes. Throughout this presentation, we will explore how this library allows us to model everything from disease outbreak using the classic SIR models to social opinion dynamics. We will take you through the theoretical foundation, the code implementation, and the real world containment strategies to show you how network social structure dictates the future of spreading phenomena. Let's dive in. Network diffusion modeling in Python, a comprehensive toolkit for simulating and studying diffusion processes on complex networks. Network diffusion. Research focus explores diffusion processes within complex networks, leveraging the powerful NDlib library for simulation and analysis. In model comparisons, it compares various diffusion models, including epidemic and opinion dynamics, to observe their unique propagation. Its core objective is its aim to understand the fundamental influence of network topology on the speed, extent, and overall trajectory of speeding phenomena. Foundations of NDlib. It built on decades of research spanning epidemiology, network science, and mathematical modeling. Understanding these fundamentals helps researchers leverage the library's full potential. Historical and theoretical roots. Roots in 1920s epidemiology, the foundational SIR model emerged from early disease modeling, establishing the mathematical framework for understanding how infections spread through population. While in graph theory and diffusion, diffusion is the governed by adjacency matrix and node state. Network topology directly determines propagation speed and extent. Dense networks spread faster while sparse networks create bottlenecks. In state transitions, the key concept is state transitions. Each node's state change based on interaction with neighbors, creating emergent dynamics from local rules. So, what are the modern applications? These classical concepts now power modern simulation of disease spread, information cascades, opinion dynamics, and innovation adoption across complex networks. So what is NDlib? NDlib is a Python software package designed to describe, simulate, and study diffusion process on complex networks. Built as an extension to NetworkX, it provides researchers with powerful tools to model how information, disease, behavior, and innovation spreads through interconnected systems. The library offers a standardized programming interface and implements a wide range of diffusion models, making it accessible for both beginners and advanced users in network science. Uses NDlib. Mathematicians. They study theoretical properties of diffusion processes and analyze network dynamics using formal models. Physicists model complex system and phase transition in network environment. Biologists simulate disease spread, genetic information transfer, and ecological interactions. Computer scientists develops algorithm for information propagation and network security analysis. Social scientists examine opinion formation, social influence in communities. Core goals of NDlib. It provides comprehensive tool for analyzing diffusion on social, biological, and infrastructure levels. Offers a consistent programming interface and implementation framework suitable for diverse applications. It creates an environment that accelerates collaborative, multidisciplinary research projects. Key features of NDlib. Its extensive model library implements classic and state-of-the-art diffusion models. Flexible network support. Work with directed, undirected, weighted, and temporal networks of arbitrary size and structure. Custom model development. Extend the framework to implement novel diffusion processes using NDlib modular architectures. Comprehensive analysis tools. Extract detailed matrices, visualization propagation pattern, and export results for further analysis. In research objectives, it investigates how network structure dictates the speed and extent of diffusion processes. It also evaluates diverse diffusion models, including epidemic and opinion dynamics for distinct propagation characteristics. It analyzes and identifies effective containment and intervention methods within various network environments. It also develops robust and accurate predictive model for real-world diffusion phenomena across complex systems. Yes, the diffusion models. Core diffusion models in NDlib. NDlib implements a comprehensive suite of diffusion models, each designed to capture different types of spreading phenomena across networks. The epidemic model. These models look at how people get sick and whether they get better. SIR. People start healthy, get sick, and then get better. Once they are better, they have immunity, meaning they can't get the same sickness again. Think of chickenpox. Second, SIS, the never ending model. People go from healthy to sick, but once they recover, they immediately become healthy and can get sick all over again. There is no immunity. Think of the common cold. Now, moving to information diffusion models. These models look at how ideas or viral news spread from person to person. I see the one shot try. When one person knows a secret, they try to tell their friend just once. Each friend has a random chance of catching the idea. Once they have it, they stay active. Think of a viral tweet. LT, the peer pressure model. A person only activates if enough of their friends are already doing it. If the influence from their friends hit a certain level, a threshold, they join it. Think of crossing or choosing to join a new social media app because of all of your friends are on it. Now the SI model, the everyone get it model. This is the simplest version. People get infected with the idea and never recover or leave. Eventually the idea spreads to everyone in the group. Think of a permanent piece of news that everyone eventually hear. Foundation built on NetworkX. NDlib extends the powerful NetworkX Python library, inheriting its robust network manipulation capabilities while adding specialized diffusion modeling functionalities. This foundation ensures compatibility with existing network analysis workflows and provide access to NetworkX extensive graph algorithm and data structures. First, network creation. Build or import complex network structures. Second, model configuration. Select and parameterize diffusion models. Third, simulation execution. Run diffusion processes with customizable parameters. And fourth, analyze and visualize. Extract insights and visualize results. Installation and setup. NDlib can be easily installed using pip, Python's package manager. The library requires Python 3.6 plus and automatically install dependency including NetworkX, NumPy, and Matplotlib. The command which we can use is pip install NDlib. Or for the latest version, you can install directly from the GitHub repository.
Using Google Colab. So we have multiple softwares, but here I am using Google Colab. So NDlib stands for Network Diffusion Library. It is an open source Python library used to model and analyze diffusion process on complex networks, such as the spread of diseases, information, and influences. So let's dive into it. So first I am searching here Colab and new notebook. So first I open Google Colab and create a new notebook. Google Colab provide a cloud-based environment where we can run Python code without installing software locally. So here what we get our notebook. Since NDlib is not pre-installed in Colab, I install it using pip. I run command pip install NDlib. Okay, so the installation is successfully. Here you see. So next I import some important libraries for network creation, NDlib for diffusion, modeling, and matplotlib for visualization. So one by one I am importing here. So our first import is network X. Import network X as NX. After that, what model we are choosing here is epidemic. For epidemic, we are importing epidemic model here. Import ndlib.model.epidemics epidemic as EP. After that, we need to import model configuration. Import ndlib.model model config as EP. And we have some other imports. For example, matplot import ndlib plotlib dot pyplot for plotting the graph as plot. And for animation, we have some other imports. For example, we have for animation from matplotlib dot animation import function animation. Okay, so that's it. After that, we need to run this. Okay, successfully run. Now I create a random network using the ADOS Renai graph model. This network will represent the structure on which diffusion take place. So I am writing the code of that model. So for creating the network, we are using this line of code here. G, our network, NX, ADOS Renai graph. And now we run this. And now we are creating the model. So for creating the model, we need to show the line. uh, we need to show the line where we giving the some parameter name like beta, gamma, and fraction. Okay, so I give all the parameters here and config So what I do here, first I give the model parameter name beta 0.9, gamma 0.1 and fraction infected 0.25. So now I run this. Okay, so I get some error here. So I configure the error. Now it was full code. Next, I run the simulation. So I write the next part of code. So what I was doing here, I run the multiple iteration. At each iteration, the model update the states of nodes. So finally, we get this is a live animated simulation graph. The x-axis represent iteration and the y-axis represent the number of nodes. This, this susceptible curve decreases as nodes become infected. This orange one is infected. The infected curve rises, initially reaches a peak and then decrease as a recovery occurs. The recovered curves increases continuously. See this line. And this was the final output. So finally, the conclusion is in this demonstration we successfully installed NDlib on Google Colab, created a network, configured on SIR diffusion model, and visualized the simulation. This shows how NDlib can be used to study diffusion behavior in complex network.
Methodology. Our approach to analyzing network diffusion processes follows a rigorous four-step methodology designed to ensure robust and reproducible results. Four steps are data cleaning, model configuration, multi-iteration Monte Carlo simulation. Fourth one, the trend analysis. In data cleaning, we prepare and validate network data by removing duplicates, handling missing values, and standardizing nodes edge attributes, ensure data integrity and consistency across all network representations before simulation begins. Model configuration, also known as parameter tuning. Select appropriate diffusion models and systematically tune parameters such as transmission rates, recovery rates, and activation thresholds. Use sensitivity analysis to identify critical parameters and their impact on diffusion dynamics. In multi-iteration Monte Carlo simulation, we execute multiple simulation runs, typically 100 to 1000 iterations, with randomized initial condition to capture stochastic variability. Monte Carlo provides method which provides statistical confidence in results and enable robust estimation in diffusion matrices. In the fourth step, that is trend analysis, we analyze temporal patterns and statistical trends in simulation outputs. Extract key metrics including infection curve, peak infection time, final attack rate, and network level statistics. Visualize results to identify patterns and validate theoretical predictions. This methodology ensures comprehensive understanding of diffusion process while maintaining scientific rigor and reproducibility across different network topologies and model configurations. Experimental setup. Experimental configuration. Our research environment is configured to support large-scale network simulation with optimal performance and reproducibility. Hardware specifications: 16 GB RAM to enable handling networks with 100,000 plus nodes. Processor: Intel i7 for processing for parallel simulations. Storage: SSD for fast input-output operations. Software stack: Python 3.10, NDlib 1.1.4, NetworkX 3.x, NumPy, Matplotlib, or Seaborn for visualization and analysis. Quarantine and containment analysis. Modeling disease control. NDlib enable researchers to simulate quarantine strategies and containment protocols for infectious disease. By implementing SIR models with intervention parameters, user can test various containment scenarios. Key analysis capability include comparing different quarantine threshold, evaluating contact tracing effectiveness, modeling resource allocation strategies, simulating vaccination campaign. Early intervention can reduce final infection rate, 3x reduction in spread, 40% resource efficiency, targeted quarantine versus mass isolation, 2.5 reproduction number, effective reduction with containment.
Quarantine and contamination analysis using NDlib is one of the applications of NDlib tool. In this application, we will consider three cases: no quarantine, random quarantine, and targeted quarantine. As you can see, the no quarantine, there is an uncontrolled spread. In uncontrolled spread, we have a high degree of nodes. Each node is somewhat connected to other, and this increases the infection rate. In random quarantine, if we somewhat quarantine a person randomly, there is a partial contamination of the infection, but is but it still has high degree of node as compared to targeted quarantine. In targeted quarantine, there is a strong containment of the infection, and degree of node is low as compared to random quarantine. Infection over time in no containment, high peak, random quarantine, medium peak, and targeted quarantine, low peak. We will see Python implementation of the quarantine and contamination analysis using NDlib. First, we will pip install NDlib. Then, we will import network X as NX. Im import network lib ndlib dot model dot epidemic as EP. Import ndlib dot model configuration as MC. Import matplotlib and import random. As we can see, NDlib is getting installed. Then we will create a contact network. Scale-free network realistic for social contacts. G is equals to nx dot Varabasi Albert graph, where n is equals to 50, m is equals to 2. Then we will set up SIR model setup function. SIR model in NDlib library is an epidemic simulation model that tracks the flow of individual through three states: susceptible, infection, and removed. The library allows user to define the network structure, configure the model parameters such as beta and gamma, run simulation, and visualize the result. S. Individual who is susceptible, as individual who can contact the disease. Infected, individual who has the disease and can transmit it. And removed, individual who have either removed or died or can no longer be infected or infect others. Beta, the infection probability, the likelihood that a suspected node becomes infected upon contact with an infected one during an iteration. Gamma, the removal probability, the likelihood that an infected node moves to removed state in single iteration. Using the SIR model in NDlib involved defining a network, configuring configuring a parameter beta, gamma, and initial infected fraction, running the simulation and visual the result. The library simulates the spread of disease on a network structure, including the tool for visualizing the result. We can see that we have taken gamma as zero point 0.3 and beta as zero point 0.3 and gamma as 0.05 and fraction infection as 0.05. The model.set initiate configuration in iteration model.iteration 1 is 50. No containment. And after that a random quarantine. G rand is equal to G dot copy random node is equals to random sample. Then after that we will perform targeted quarantine. High degree nodes. Then after that we will plot the before and after quarantine graph of all the three cases. As we can see that no quarantine, the infection is spreading rapidly and the degree of nodes is high. In random quarantine, there is a partial containment of the infection but still spreading fast. And in targeted quarantine, there is a we can contain the infection and degree of nodes is low. Extract the infection curve. Now we will compare the epidemic spread of all the three cases. As you can see, no containment, the peak of the graph is highest, and in random quarantine, it is somewhat close to no containment, and in targeted quarantine, the peak is the least.
Intervention effectiveness. NDlib's simulation capabilities allow for detailed comparative analysis of various public health interventions, providing insights into their potential impact on disease spread and resource optimization. This bar chart illustrates the simulated impact of different containment strategies on reducing the peak infection rate within a population as modeled using NDlib. Baseline, no intervention. The peak infection rate remains at its highest. Targeted efforts, combining contact tracing and moderate quarantine measure, significantly flattens the epidemic curve. Combined strategy, the most effective approach involves a synergistic combination of aggressive quarantine and comprehensive contact tracing, leading to a 80% reduction in peak infection. Such simulations empowers policymakers to anticipate outcomes and implement data-driven public health responses.
We will see application of the NDlib tool, which is modeling meme spread on social media using NDlib. The objective of the application is to simulate and analyze how memes spread across a social media network using diffusion model and compare the random memes seeding, influential based seeding. Tools and technology which we are going to use in this application are Python, Network, NetworkX, NDlib, matplotlib. First we will pip install NDlib and import network xsnx and import network ndlib.model.epidemicsed and import matplotlib import random. As you can see that we have installed the NDlib. Now we will create a social media network using Barabasi Hilbert graph and take n is equals to 200 and m is equals to 3. After that, we will create a function to run meme spread. After that, scenario 1, random user start meme. A random user starts a meme and we write the function for that. And second scenario, influencer start meme. Now we will compare plot as you can see that meme spread started by influencer has a higher peak as compared to random users. The summary of the modeling meme spread on social media using NDlib. This explores how memes spread across social media network using diffusion model for the NDlib library. The social network is modeled as a scale-free graph, such as Barabasi-Albert model, which reflect real-world platforms like Instagram or Twitter, where a few influencers have many followers. The independent cascade model is used to simulate meme sharing behavior. In this model, when a user share a meme, they get a single chance to influence their connected neighbors to share it as well. Two scenarios are analyzed in this application: random seeding. Meme starts from a random selected users, and the other scenario is influencer seeding. Meme starts from highly connected user. The simulation results show that influencer-based seeding lead to faster and wider meme spread compared to random seeding. This demonstrates the importance of network structure and highlights how targeted marketing strategy can significantly increase virality. Overall application instructs how network science and diffusion modeling can be applied to understand the information propagation and optimize the digital marketing strategies.
Its advanced research applications. Opinion dynamics model how opinion and beliefs spread through social networks, examining polarization and consensus formation. Information cascades study viral content propagation, meme diffusion, and information overload in online platforms. Innovation adoption simulates how new technologies and ideas diffuse through social networks and markets. Financial contagion. Analyze risk propagation in financial networks and systematic vulnerability in economic system. Future research directions. Our research roadmap includes several promising extensions and enhancements to advanced network diffusion modeling and analysis. Multi-layer and temporal networks. Integrating NDlib with multi-layer temporal graphs to model complex real-world systems where the networks evolve over time and contain multiple types of relationships. This enables simulation of dynamic network where node connectivity and edge weights change throughout the diffusion process. Deep learning for diffusion prediction. Applying deep learning to predict diffusion paths and outcomes. Neural networks can learn patterns from simulation data to predict infection curves without full simulation, identify critical node for interventions, forecast cascades outcome in real time, optimize containment strategies. Additional future directions: heterogeneous node edge attributes, adaptive intervention, hybrid models, GPU acceleration, real world validation, interactive visualization. Develop web based tools for exploring diffusion dynamics. These extensions will enhance NDlib capability to address increasingly complex real-world problems in epidemiology, social networks, and complex system research. Options. NDlib represent a powerful and accessible platform for understanding diffusion processes across complex networks. Throughout this presentation, we have explored how this Python library bridges theoretical foundations and practical applications. What are the key takeaways? Comprehensive modeling. NDlib provides a unified framework for simulating diverse diffusion phenomena, from epidemic spread to information cascades, enabling researchers to test hypotheses efficiently. Accessibility and reproducibility. Built on Network X and Python, NDlib democratizes network science research, making advanced simulation available to researchers worldwide with transparent reproducibility workflow. Real world impact, from quarantine strategies to opinion dynamics. NDlib applications address pressing challenges in public health, social network, and complex systems. Extensibility. The library's modular design supports integration with emerging technologies like deep learning and temporal networks, ensuring relevance for future research. Our work demonstrates how systematic methodology, combining data cleaning, parameter tunneling, and trend analysis, yields robust insight into network diffusion dynamics. The convergence of NDlib with multi-layer networks, deep learning, and real-world data opens unprecedented possibilities for understanding and predicting diffusion phenomena in increasingly complex systems. Our team encourages researchers, practitioners, and students to leverage NDlib for their own investigations. The open source community continues to expand the library's capabilities, making it an essential tool for network science in the 21st century. NDlib, modeling the future of network diffusion. For your time and attention. We hope this presentation offered valuable insights into NDlib's network diffusion modeling capabilities.